Hello everyone and welcome back to Unit 6, Unbalanced Forces. In this video we are going to do the part 1 of problem solving. Remember, anytime we do problem solving we want to remind ourselves of the problem solving process, which is 7 steps. We should be very familiar with it, and those 7 steps are as follows. Step 1, we want to draw a picture, and anytime we're dealing with forces, that picture is our free body diagram. So we're going to continue to draw those in this unit to show all the forces that are acting on an object, which of those forces are balanced, or in our case, unbalanced for this unit. Step 2, write the givens with the number, unit, and symbol. Step 3, write the unknowns. We're very familiar with those 2 steps. Step 4, picking an equation to solve for the unknown. Sometimes we have multiple equations that we're dealing with. In this unit, we will be using those component equations that we learned in the last video. So Fx, or the force along the x-axis, is equal to the force on the hypotenuse times the cosine of that angle. Fy, or the force on the y, is equal to the force on the diagonal times the sine of that angle. So we got some practice last time with those equations. We might need to use them. Since we're also dealing with unbalanced forces, we are going to need Newton's second law, which is Fu equals ma. A lot of times we will be solving for that acceleration in these problems in this unit, so we're going to need that equation. And remember, sometimes we might be using multiple equations, and that's okay. Step 5, rearranging the equation if necessary. Step 6, checking our units. And step 7, solving the equation for the unknown. So in this video today, we're going to start with a simple example, kind of getting used to this Fu equals ma business, and then we'll move on to a more complex example where we need those vector component equations. So let's get started. So our first example is finding the unbalanced force. So Miss Nielsen is pushing a 25 kilogram box to the right across carpet with a force of 38 newtons. The normal force exerted on the box by the floor is 245 newtons, and the coefficient of friction between the box and the floor is 0.12. What is the unbalanced force on the box? So first step, we're going to just draw our picture, draw our free body diagram for this scenario. So we have a box, we're drawing a box for our box. We know that this box is on Earth, so obviously we have the force of gravity that's going to pull it straight down as usual. That is the weight of the box. Okay, we're also it's also sitting on the ground. There is a normal force, we know that, it tells us that. So the normal force is going to be pointing straight up. That's our normal force, supported by the ground. We know that the normal force and the force of gravity are equal and opposite in this case. So we're going to mark that those are equal. We also know that I am pushing the box to the right. There's an applied force to the right. And finally, we know that there is friction. There's friction between the box and the floor. They tell us that. So that means friction is going to be opposite of the motion. So if I'm pushing it to the right, it's moving to the right, so friction is going to point to the left. So we're going to put the force of friction pointing to the left. There it is. And I drew it small, and you'll know why I drew it small here in a second. But like I said before, we know that the normal force and the force of gravity are equal and opposite. So I'm going to write that relationship, that Fn is equal and opposite to Fg. We're going to put those hash marks in our drawing. However, the force of friction and the applied force are not equal and opposite, okay? Actually, the applied force is going to be bigger than the force of friction. The reason why that is because we're in the unit of unbalanced forces. We're always going to have a force that's bigger in one direction compared to the other direction. So we'll talk more about that. I'll prove it to you why that force is bigger here in a second. Moving on to step 2, to write down our givens. I am pushing the box to the right across carpet with a force of 38 newtons. So 38 newtons to the right is my applied force. So 38 newtons, to the right, we gotta write that down. Right is equal to my applied force Fa. Also, it tells me in there the mass of the box is 25 kilograms. Remember, kilograms is the unit for mass. The next number that we see is that the normal force exerted on the box by the floor is 245 newtons. So 245 newtons pointing upwards, right? Our normal force points up. That's equal to Fn. And then finally it tells us that the coefficient of friction between the box and the floor, there it is, coefficient of friction between the box and the floor is 0.12. So that's our final number that we're given. 0.12 is equal to the coefficient mu. So moving on to step 3, what are we looking for? What's the unknown? Well, the question asks us, what is the unbalanced force on the box? So we are looking for Fu. Fu is equal to question mark. Okay, so when we move on to our next step, step 4, picking our equation. This is a little bit tricky. We have a lot of equations from last unit and our additional component equations from this unit that we talked about in the last video. Remember, our Fu equals ma is kind of our primary equation for this unit, but we do need some of those component ones sometimes. But in this situation, if we're trying to find the unbalanced force, we might think that we would use that equation, Fu equals ma. But we don't know what the acceleration is. We're given the mass of the box, but we don't know what the acceleration is. So finding the unbalanced force, we're actually going to use that relationship there. We know that Fn is equal to Fg, but we know also that Fa is greater than the force of friction. So to find the unbalanced force, it's just the difference between those two forces. So whoever's winning minus the other force, that's going to be our unbalanced force. Because remember, the unbalanced force is just in the direction of who is winning, and it is quantified, it's the number of it is how much they're winning by. Okay? So the difference between those forces is going to be our equation for our unbalanced force. Remember, we're just finding it based on those relationships between the forces. There's no unbalanced force up and down, it's just left and right that we're concerned with. So that's how we're going to find our unbalanced force. We don't have to rearrange our equation since we're looking for the unbalanced force, and we made up that relationship there. Step 6, we're going to check our units. So the units for unbalanced force, well, our units for applied force is newtons, and the units for the force of friction are also newtons. So ideally, our unbalanced force should be measured in newtons because it's a force. All forces are measured in newtons, and we do get that newtons minus newtons is still newtons. So that works. So step 7, actually, if we want to solve for the unbalanced force, we have to know what is the applied force and what is the force of friction. We don't know what the force of friction is. We know the coefficient and we know our normal force, so we can find the force of friction. Remember, with that equation, force of friction is equal to the coefficient, mu, times our normal force, Fn. So we're going to use this equation. This is more of a sidebar solving for this problem. We're going to use that equation first to find the force of friction, and then we'll plug it into that first equation to find our unbalanced force. So the force of friction should be equal to the coefficient of friction, which is 0.12, and we're going to multiply that by the normal force, which is 245 newtons. And when we plug that into our calculator, we find that the force of friction is equal to, 29.4 newtons. That's our force of friction, and it's pointing to the left. Okay, we know that from our free body diagram. It's opposing the motion, so it's to the left. Okay, but we're not done yet. Remember, we're trying to find the unbalanced force. So now we know that our applied force is 38 newtons to the right, and our force of friction is 29.4 newtons to the left. So now we can use that equation to find out what's the unbalanced force. How much is the winner winning by? How much of a lead do they have? Okay, so 38 newtons minus our force of friction, which is 29.4 newtons. We find that our unbalanced force is 8 0.6 newtons. Again, just simple subtraction there. And our unbalanced force is in the direction of the winning force. So in the tug of war, our applied force is winning, which is pointing to the right. So our unbalanced force is going to be pointing in that same direction to the right. And that is our problem. Again, we didn't use a specific equation to find the unbalanced force. We just wanted to find what is the difference between the two forces in the tug of war. Okay, because we knew our applied force had to be bigger than the force of friction, otherwise the box wouldn't even be moving, right? So we had to find what the difference between those two forces was. That's our unbalanced force. Again, because our forces were not balanced. We knew our applied force was bigger than the force of friction. And this is not uncommon. We're always gonna have to find what the unbalanced force is. Okay? So here's another example. Mr. Willauer is pulling his cat in a sled across the snow. He is pulling on the sled rope with a force of 18 newtons at an angle of 40 degrees above the horizontal. There is a small force of friction of 7 newtons to the left. What's the unbalanced force on the sled? So we're starting out with our free body diagram. Here is the box that represents the sled with the cat on it, I guess. We know that this sled is on Earth, so we're going to have the force of gravity pulling down. We also know that the sled is sitting on the ground, so there is a normal force. I'm not going to draw it yet, and we'll talk about that in a second. We know that there is force of friction to the left, so we're assuming that Mr. Willauer is pulling his cat to the right. He's pulling it with a rope at an angle of 40 degrees above the horizontal. Okay, so now we're going to have to do a little bit of trig stuff, which we talked about in the last video. But basically he's pulling up at an angle to the right with a force of tension because he's pulling the rope. Remember, ropes have tension, and he's pulling at an angle of 40 degrees above the horizontal. So up and to the right. Okay, we also know that there's friction pointing back to the left, so there's a little bit of friction. It says that there's a small force, so I'm going to draw a small arrow. And like I said at the beginning, we also know that there is a normal force. But usually we draw the normal force is equal and opposite to the force of gravity. But it can't be equal in this case, and I'll show you why. If we have the force of gravity pulling down and the normal force is equal and opposite to that, take a look at how the tension force is also pulling up. Okay, so if we had equal and opposite normal force and gravity, and then we also had the force of tension is pulling up a little bit, then this sled would be like flying up in the air. There'd be an unbalanced force pointing up. And that's not what's happening. We know that the sled is going to glide across the snow to the right. Okay, so we can't have that scenario. So our normal force actually has to be smaller than the force of gravity because we are pulling up on the sled so that the ground doesn't have to do as much work to support it. Okay, that's a small little technical thing, but it is really important to talk about. So moving on to our step 2, we're going to identify all of our givens. We are looking for the unbalanced force in this case, and we will have to use some of that trig, so Fx and Fy, but we'll get to that later. Identifying our givens, the first thing that we see is that we're pulling on the sled rope with a force of 18 newtons at an angle of 40 degrees above the horizontal. So our 18 newtons, that is our applied force, or our tension. Either one would work in this case. And our angle is 40 degrees, again, above that horizontal. So up and to the right. We also know that there's a force of friction of 7 newtons to the left. So 7 newtons left is equal to the force of friction. And actually those are the only things that were given in the problem, which you might not think is enough information, but it is. It's going to give us exactly what we need to solve it. So step 3, identifying the given, we already said that we're looking for that unbalanced force. What is the FU in this case? And we're going to do something very similar what we did last problem in terms of our equation. We're going to figure out which force is winning and how much it's winning by. Okay, we're going to assume that the force of tension is winning against friction, because Mr. Willauer is pulling it to the right and he's pulling it up. So we're assuming that that X component is going to be bigger than force of friction, otherwise the sled wouldn't move. Okay, but we know he's pulling his cat, he's actually moving it. Okay, so I'm drawing right there, we've got our two components of tension. We have tension pulling to the right, we have tension pulling up. So we're also going to need to find what is Fx and what is Fy. Again, we need to know what Fx is because we need to know if it's bigger than friction, because friction is pointing directly back to the left. We need to know what is pulling directly to the right. So step 4, we're actually going to find our components first, our Fx and our Fy. What are those first? And then we'll worry about the unbalanced force. So our Fx, remember, is equal to the force on the diagonal, which is tension in this case, times the cosine of our angle. And similarly, our Fy is equal to the force on the diagonal, which is the force of tension, times the sine of our angle. So we can solve these really quick. Actually, we know that we're going to get, our units are going to work out. We don't have to rearrange them. So why don't we just plug this stuff in right now. Show you our triangle real quick. We have Ft. We know that it's equal to 18 newtons. That's our force on the diagonal. We have our Fx, which we're trying to find. How much is Mr. Willauer pulling directly to the right? And then we have our Fy. How much is Mr. Willauer pulling directly up? We got that right angle, and the angle that we're concerned with is our angle above the horizontal, which is in the bottom left corner of our triangle, which we know is 40 degrees. So as I said before, our tension is equal to 18 newtons. That's how much Mr. Willauer is just pulling. We're trying to figure out how much is he pulling to the right, how much is he pulling up. Okay, so we're going to plug in our 18 newtons for tension times the cosine of our angle, so cosine of 40. When we plug that into our calculators, we are going to see that Fx is equal to, let's see, 13.8 newtons, and that is to the right. Okay, we know that's to the right, that's because of our drawing. Same thing with Fy, we're going to plug in our 18 newtons times the sine of 40, and we will find that our Fy is equal to, let's see, 11.6 newtons. Okay, so our Fy is pointing directly up, and our Fx is pulling to the right. Okay, we said that before. So now, when we're considering the unbalanced force, okay, up and down, we are assuming that those are going to be equal. Everything up is going to be equal and opposite to everything down. But remember, our force of friction is 7 newtons to the left, and our applied force directly to the right, our Fx, is equal to 13.8 newtons. So we know right away, looking at that drawing, we have the fact that Fx is bigger than Ff. So the tension that Mr. Willauer is pulling directly to the right is bigger than the force of friction pulling back to the left. So our unbalanced force is going to be equal to Fx minus the force of friction. So step 5, we don't need, again, because we're just solving for the unbalanced force. So step 6, again, to check, our Fx is measured in newtons, okay, and then we're subtracting the force of friction, which is measured in newtons, so our unbalanced force is also going to be measured in newtons, okay, which is good. The unbalanced force is a force, so it should be measured in newtons. That works out. Number 7 here, step 7, plugging in, our Fu is equal to our Fx, which was 13.8 newtons, right there in our free body diagram. 13.8 newtons to the right. It's winning against friction. Friction is only 7 newtons back to the left. So we're going to find the difference between those two forces. That's our unbalanced force. So our unbalanced force in this case is 6.8 newtons. I think we had 8.6 before, now it's 6.8. Imagine that, okay? Our unbalanced force is in the direction of the force that's winning. Again, our force that's winning is Fx, which is pulling to the right, so our unbalanced force is to the right as well. So a little bit more of a complex problem than the last one, but the general process was the same for finding the unbalanced force. Okay, we take the difference between the two forces that are not balanced. That's our unbalanced force. That's the leftover. Okay, that's how much the winner is winning by. That's how much the lead that they have. So our final example is finding acceleration. So Miss Nielsen's car is stalled, so she puts it in neutral and gets out and starts pushing. The car has a mass of 1250 kilograms, and Miss Nielsen pushes on the car to the left with a force of 250 newtons. If the force of static friction acting on the car is 245 newtons, what's the car's acceleration? So first step, again, free body diagram. That box represents my car. The car is on Earth. So again, we have the force of gravity pulling down. We're going to wait on the normal force. We'll fill out our other ones first. It says that I am pushing on the car to the left with a force of 250 newtons, so that's going to be an applied force to the left there. Also, we know that there is static friction on the car. Static friction is just the friction that's acting when something isn't moving. So that force is resisting my push to the left, so it's pushing to the right. If the car was moving, it'd be pushing to the left, so friction acts to the right. And then, of course, we have the normal force that points up. In this case, the normal force is equal and opposite to gravity because it's not like we saw in the last example where the applied force was on an angle. Now we have our applied force straight to the left, so the normal force is going to be equal and opposite to gravity, is what I'm trying to say. Also, if we notice here that I am pushing on the car with 250 newtons, and friction is pushing on the car with 245 newtons. So we have an unbalanced force. I am winning this, this tug of war against friction. So the applied force is going to be bigger than the force of friction. Okay, so that is going to be how we determine our unbalanced force, that inequality there. Step 2, we're going to identify all the givens. So the first given that we have in the problem is that the mass of the car is 1250 kilograms. So 1250 kilograms is equal to the mass M of the car. Next up, it says that I am pushing the car to the left with a force of 250 newtons. So 250 newtons left is going to be the applied force. So FA, that's equal to FA. And again, it's pointing straight to the left. There's no angle business. We don't have to worry about the components. Finally, the force of static friction acting on the car is 245, and we already determined that that is pointing to the right. So 245 newtons to the right, because I'm pushing on the car to the left, so friction is resisting that motion back to the right. Okay, those are all the numbers that were given in the problem. Step 3, it's asking what is the car's acceleration. So A is our unknown. What is the acceleration of the car? So step 4, now to identify which equation we're going to use. Well, now we're actually going to use this Fu equals ma equation, because we're first going to find what our unbalanced force is, and then we'll be able to find our acceleration from it. So we're pretty comfortable now with finding our unbalanced force. We take a look at which forces are unbalanced, and we subtract the two. So we take the winner and we subtract the other force. So my unbalanced force is going to be equal to my applied force minus the force of friction. So that is my other equation that I'm going to use to figure out my unbalanced force. Step 5, rearranging. We actually do need to rearrange. We won't need to rearrange that equation, but when we plug in the unbalanced force into our Fu equals ma, we will have to rearrange, okay? We want to solve eventually for acceleration. Like I said, we'll have the unbalanced force. We want to solve for acceleration. So I want to rearrange it so that acceleration is by itself. So I want to move the mass over to the other side. So I'm going to divide both sides by the mass. It cancels there on the right side. And I'm left with that the acceleration is equal to the unbalanced force minus the mass. Or divided by the mass, excuse me. Unbalanced force divided by mass. Units, we've checked the units for our unbalanced force equation a couple times. We know that applied force is in newtons and the force of friction is in newtons, so our unbalanced force will be in newtons as well. We know that. But now we're going to check our units for acceleration. So the units for acceleration should be the units for unbalanced force, which is newtons, divided by the units for mass, which is kilograms. And a long time ago when we talked about newtons, we discovered that 1 newton is equal, it's the same thing as a kilogram times meter per second squared. That's what a newton is. So if we take that and we divide by kilograms, you can see that the kilograms cancels out, and we're left with our unit for acceleration, which is meters per second squared. Okay, which that is our unit for acceleration. So that's good. We got what we wanted to. We did our rearranging correctly. Now we're going to plug in and chug and solve this problem. So Fu, we're going to find that first, the unbalanced force. We're going to take our applied force, which is 250 newtons to the left, and we're going to subtract the other force in the tug of war, which is 245 newtons to the right. We're going to subtract those, and we see that for our unbalanced force, we get 5 newtons. And again, it's in the same direction as the winning force, which is the applied force, which according to our free body diagram is to the left. So our unbalanced force is 5 newtons to the left. And now we can easily find our acceleration. We're going to take that unbalanced force of 5 newtons. We're going to divide by the mass, which is 1,250 kilograms. 5 divided by 1250 is going to be a really, really small number. So we get, for our acceleration, we get 0.004 meters per second squared. That's really small. Our acceleration is in the same direction as the unbalanced force, which is to the left. Okay? If I am pushing the car to the left and I am winning the tug of war, the car will accelerate to the left. That's a really, really small acceleration, but think about how big a car is and how small my pushing abilities are. So really, in reality, that kind of makes sense. It'd be accelerating really slowly. It would take me a long time to get this car up to speed so that I could actually end up driving it successfully. Okay? So again, the key here is really just finding that unbalanced force. That's our first step. And then once we have that unbalanced force, we understand the relationship. We might need to use those component equations that we talked about in the last video. But once we find our unbalanced force, it's really easy for us to find that acceleration. Okay, and our unbalanced force, again, it's just the leftovers from the tug of war. How much is the winner winning by? What's the difference between those two forces? Okay, and we'll get lots more practice with unbalanced forces and acceleration in the next video as well.